Well, welcome to Chapter 3, Seasonal and Daily Temperatures, Causes and Effects in the Earth's Atmosphere. This is a part of ESCI 211, Chapter 3. So, what should you have a better understanding of at the end of this online lecture? The effects of the seasons. Or I should say, what affects the seasons. You should know how the Earth's orbit affects the seasons and how the Earth's tilt affect the seasons. What local condition, or I should say, what local conditions can affect the temperature, the effect daytime has on temperature, and the effect nighttime has on temperature. How do you take a temperature, particularly the atmosphere? What controls the temperature? The four main things that control temperature that you should be aware of are latitude, land and water, ocean currents, and elevation. What is an isotherm? What temperature data is recorded, or I should say how temperature data is recorded. Other factors that can affect your sense of temperature, and instruments used to measure temperature. Let's get started. Okay, so normally students have two answers to this, um, and let's talk about the effects of the Earth's orbit. So if you look at this, we have the Earth orbits here. It's not a circle; it's actually an ellipse. It's a really close circle, but not a circle. So in the middle of winter in January, the sun is 47 million kilometers from Earth, and in summer it's 42 million kilometers. So when is it closer to the sun? When is the Earth closer to the sun? So if you think about it, it's farther away in the summer. So how can it be warmer here, warmer in the northern hemisphere in the summer, and when it's farther away from the sun? Well, the main reason for this is the orbit does not have much effect on the seasons. What affects the seasons are, I should say, is the tilt of the Earth. The Earth's axis here is tilted by 23.5 degrees. This tilt causes summer, or the start of summer, June 21st, is you have what's called the summer solstice, which is the sun is directly over 23.5 degrees north latitude, so right about here. And then you have winter solstice when the sun is directly over the same direction of the southern latitude. And that's when winter occurs, is when the sun is over that part of the latitude, or what high noon is there. And then you have equinoxes. You have the spring equinox or the vernal equinox, and that's at March 20th. The sun shines directly over the equator. And then you have the autumnal equinox. Again, the sun shines directly over the equator. So as the Earth goes around the sun, its axis always points in the same direction. Okay? So when it's summertime, the sun is here, points here, okay? And when it's wintertime, the sun is hitting this part of the globe, and then the Earth spins on its axis. So there's this phenomenon in the autumn here in North America that you can get what's called Indian summer. It's a time in the autumn where the temperatures get up close to the normal summer temperatures. Alright, so let's look at how the sun affects the Earth's temperature. Now, when the sun is directly over the equinox here, just like this line shows how much of the sun's energy is hitting the top of the atmosphere. This shows how much of the sun's energy actually reaches the surface. And you can definitely see over this latitude right here that more energy is coming in at this point right here. Less at the poles because there's a higher albedo at the poles, and then less at the equator at this particular time of year. But this is happening, I believe, in near summer equinox. All right, so here's how the tilt affects summer and winter. So if you look at these lines here, the thing is, if you look at up here at the pole, the North Pole here, and this would be summertime, you can see that the sun's rays get spread across this area here, but down here, the sun's rays are spread over a much smaller area. So there's more energy per unit area down here than up here. So this is why the poles are always colder. It's the same amount of energy that comes in hits the part of the atmosphere, but it gets spread over a much larger area. And another reason the poles are colder is because there's a higher albedo because of the snow on the ground. But down here, it's a much smaller area, so you have more energy being put in per unit area. Now, in the wintertime, what happens is the sun's coming in from this direction, and you'll see that you still get the same occurrence right here. So you get summer in the southern hemisphere and winter north, but up here you get more. The sun is spread over a bigger area, so it has more energy per unit area, and or I should say, there's less energy per unit area. So less energy per unit area usually correlates to lower temperatures. So this is why we have seasons on the Earth. If the Earth's axis was pointing straight up or down, we would have no seasons. We'd have the same weather year-round. But in our case, it's not. It's tilted, so we get our seasons. So another effect, I think we've seen this before in the energy budget, is the equator has a surplus of energy over a full year, where the poles have a deficit of energy. Okay? And so what happens is the heat is transferred from the equator to the poles. Alright? Now, you can have what is referred to as local variations of temperature. So basically a southern exposure or a northern exposure. So if you have a house, the southern exposure of the house is usually warmer when the sun's up. Or should we say a southern exposure of a hill. On the southern side of the hill, if we're in the northern hemisphere, it's usually drier. There's usually less vegetation, and there's longer growing seasons since it's warmer. Or more energy gets pumped into there. It usually gets a longer growing season. On the northern exposure of a hill, you usually have more vegetation because it's a little cooler and climate, and there's usually not as dry, so the vegetation grows more. And then snow lasts longer on the northern side because it's in the shade more. It's shaded more from the direct rays of the sun. It's just like snow does not melt as fast when it's in the shade as it does when it's in the sun. Alright, so we have daily temperature fluctuations. So in the daytime, we're exposed to the sun. So we get heating from the sun. So the sun's rays come through the atmosphere and heats the surface first, okay? but air is a poor conductor, so that heat stays at the surface. So the surface is usually warmer. And if you look at this, it's only like 3 meters difference going up, but you can have as much as 20 degrees Celsius temperature difference is 3 meters up in a calm afternoon. But if it's a windy afternoon, the atmosphere is is mixed better, so the warmer air gets mixed up with the cooler air above, and so you get a different temperature profile. You get a much linear curve. So on a calm day, you get a quadratic temperature, or it's a curved temperature lapse rate, and in the windier days, you get a more linear because there's more convection going on. So here's a question for you. Why is it warmer at the ground? Okay, so the reason it's warmer at the ground is land has a lower specific heat. So if you put the same amount of energy into land, you'll have a larger temperature rise. Now, it's warmer at the ground also because air is a poor heat conductor. It's a gas. The molecules are not close together, so the heat that's in the ground will not be conducted up into the atmosphere that quickly. So all that energy stays lower on the ground. And so it warms up the temperature on the ground. That's why it's warmer, always warmer on the ground. Alright, so when do we have a maximum daily temperature? It's interesting that here we have a graph of the energy rate and temperature here, and here we have a graph of the time throughout the day. So we have sunrise, and we see incoming energy, and as the energy comes in, the Earth outputs more energy also. Okay, but look at the temperature. So we have a minimum at sunrise and a maximum at about 4 p.m. But when is the energy a maximum? That happens, the energy input happens around noon when the sun's directly overhead, or as close as overhead as we can have at that time of year. And then its energy input decreases. The Earth's energy input hits a max, and then it starts to decrease a little bit until until the sun comes up, and we repeat. So here's another question for you. Why is there a lag in the temperature and the maximum energy input? Okay, so the reason for the lag is, it's very straightforward, is air is a poor conductor. So at noon, the ground will be the warmest because it has the greatest energy input, but it takes time for this energy to conduct upwards since air is a poor conductor. So it takes about, on average, 4 hours. If it's windier, it'll take probably a little less because the air will be mixed together better. Alright, so what are some other daily effects? Well, you can have clouds. You know, if you have clouds, the temperature is usually cooler because it keeps the sun from hitting the ground. It also can be affected by large bodies of water, vegetation, and soil. And it can be affected by humidity. It's affected by large bodies of water because of the specific heat of water. The specific heat of water is high compared to that of land, so it takes more energy to get the same temperature change in for water than it does for land. And then vegetation can affect it, and soil exposure can affect the daily temperature. The more vegetation you have, the smaller the temperature change. And then humidity, the amount of humidity is also can affect how high the temperature gets. Now, we'll talk about what happens in the night. When the sun goes away, the Earth still has energy, and you have what is called radiational cooling. The Earth will emit infrared radiation out into space, and this cools off uh, the atmosphere. It also produces what's referred to as a radiation inversion, and we'll talk about that here in a bit. All right. So here is the temperature profile with altitude versus temperature for nighttime. You'll see that as you go up in altitude now, the temperature can increase. And if you have a calm night, you're going to have a quadratic function or a curved function of temperature as you go up. And if it's windy, it's going to be better mixed atmosphere, so you have a linear lapse rate. Now this is, as you go up, it warms, and that's called a temperature inversion. So why does this happen? Well, after the suns go down, it's been down for a while, the air that has been heated near the surface has time to convect or conduct upwards, and that air will conduct upwards, so the warmer air will be on top, and the cooler air will be on the bottom at this time, because this is going to cool down faster through radiational cooling than the air. Alright, you can have what's called a thermal belt and a valley, which is, what happens is the warmer air gets trapped in the higher altitudes of a valley. The colder air is going to be more dense, so it's going to stay in the lower part of the valley, and so the warmer air will be above it because of this radiational cooling effect. It's cooler at the surface now at nighttime. The warmer air will be conducted upwards, and we'll get this temperature inversion, and this creates this thermal belt. The other things that can affect daily temperature is time, or long nights or long days. So if you have a longer night, it's going to have more radiational cooling, so you'll cool off more. Again, humidity and the same reasons for soil and vegetation. Alright, how do you take a temperature? The National Weather Service requires you take a temperature at 1.5 meters above the ground. The thermometer needs to be sheltered from wind and rain, so that keeps off the instrument, or I should say be sheltered from rain and snow, so that's off the instrument, and so that you're actually just measuring the temperature of the air. The thermometer needs to be in the shade. It doesn't want to be exposed to direct sunlight. Alright, so what are the controls of temperature? Alright, the first factor is latitude. We showed since the Earth is tilted, the farther you go to the poles, the more area the energy is put into, so there's a smaller increase in temperature. So that as you go up in latitude, the temperature cools off. Land and water distribution affects it. So if you're surrounded by land, that's a small specific heat. So they have a bigger temperature change for the same amount of energy. If you're surrounded by water, it's a high specific heat of water. It takes, if you use the same energy, you're going to have a lower temperature change there. Ocean currents. You can have warm ocean currents and you can have cold ocean currents. These currents will affect the temperature in their vicinity. If you're in a warm current, you'll have a warmer climate. If you're in a colder ocean current, you'll have a colder climate. So San Francisco has cooler weather because it's at a spot where an ocean current brings in cold water. England has a warmer climate because it's at a spot where the Gulf Stream brings up water, warmer water, to their area. And the last thing is elevation. The higher you go up in altitude, the colder the air gets. So this is the lapse rate in the atmosphere. If you go up higher in the atmosphere and troposphere, the temperature goes down. Alright, so an isotherm. What is an isotherm? That's these lines here. Specifically, this one marked 70. An isotherm is a line of constant temperature. So everything on this line has the same temperature. So you can tell here, at least in this picture, that we have the colder temperatures towards the poles. Okay, the warmer temperatures are right along the equator. It appears here the warmer temperature always in the southern hemisphere. So I think this is around January. The colder temperatures are in the northern hemisphere. You can also see that the warmer temperatures are in the oceans or near the oceans, and the colder temperatures are on land. So I think this is isotherm for winter. You can see the ocean currents here, the Gulf Stream bringing warmer air to England, warmer water to England, so on and so forth. Here's another isotherm. This one looks like this is in July, because look at all the warm weather in the northern hemisphere, and the southern hemisphere has cooler temperatures. Again, in the summer, the warmer temperatures are on land because land has a lower specific heat than water. The lands have greater temperature fluctuations compared to places near water. Alright, so let's go over the temperature controls again. Latitude, it's energy per unit area. If you're at a higher latitude, same energy but larger area. If you're lower latitude, same energy, smaller area. Lower latitudes will have higher temperature changes. Upper latitudes will have smaller temperature changes. Land and water distribution, again, is the specific heating material that affects that. Land has a small specific heat. Water has a large specific heat. Ocean currents, again, moving warm water to cool areas and moving cold water to warm areas. So like San Francisco is cold water to a warmer area, and warmer water to a colder area is like England. And then elevation. The higher you go up in the atmosphere, the colder it gets, at least in the troposphere. Alright, so we can get daily, I'll show you this better in class, but we can actually get daily air temperature isotherms, and I'll show you a location on the internet where we can find those. Alright, so there's a daily range of temperatures, and that's as defined as the difference between the daily maximum and minimum temperatures. So this question is here: is where does the greatest change occur in daily temperatures? The answer to that would be on land. The low specific heat. So the temperature can be raised much quicker and lowered much quicker. And it will also occur at the surface. Does this change depend on anything? The answer is yes. Location, conditions, and materials. Altitude also. Alright, another way to record temperature is the mean daily temperature. That's the average of the highest and lowest temperatures for a 24-hour period. And these are the temperatures that were published mostly in newspapers and radio. Another way to record it is the average temperature. The average of the mean daily temperatures for a particular day averaged over 30 years. The average temperature for each month is the average of the daily mean temperatures of the month. Okay, so you got that? So what is normal? If the normal high temperature for Indianapolis on today is actually around 36 degrees Fahrenheit. So the question is, are we going to reach that today? Alright, the difference, okay, so another way is the annual range in temperatures. That's the difference between the average temperatures of the warmest and coldest months. So, where do the largest ranges occur? Again, it's over land. The question is, why is it over land? You should have put, let's say we've got a lower specific heat. Alright, so an annual range of temperatures. Where did the smallest occur? Again, over water. Question is why? Should have answered it's got a higher specific heat. Does anything else affect it? The answer is yes. Altitude and latitude. Why? Well, latitude is lower energy per unit area, and altitude is the lapse rate in the troposphere. Alright, another way to measure temperature is the mean annual temperature, average of the 12 monthly average temperatures. So, people use this information to make decisions about what is required to do specific things in society. So heating and cooling experts use information called the heating degree day and cooling degree days. Basically, the cutoff is 65 degrees. If the temperature is above 65 degrees, that's one. If it's 1 degree above 65 degrees, that's one cooling degree day. If it's a degree below 65 degrees, that's one heating degree day. So depending on how many degrees you're above or below, could increase the number of days. So in Indianapolis, we have both need of heating and cooling, and this determines how much insulation you put in your house and how big your heating and cooling systems need to be to keep you comfortable in your home. The other way they can use this is what's called a growing degree day. Each crop has a specific number of growing degree days that it needs to get to maturity so they can harvest it. And again, they use, I believe it's 65 degrees. So every degree above 65 degrees, I should say, 1 degree above 65 degrees is one growing degree day. So you can put them all together if they need to be put all together, and determine how many growing degree days you need to grow a crop, and this would help you determine what part of the planet you would need to grow these on, or where you would need to grow this crop at. And we'll do an activity in class that helps you determine which crops work best in which areas of the country. Alright, another thing that we use is what's called a comfort factor, or what I like to call the bitch factor. It's man, it's cold out there, or the National Weather Service calls these two things, the wind chill and the heat index. This is what's called sensible temperature. So what is the wind chill index? Well, in order for our body to stay warm, we need to keep a layer of air around our body, because that's a good insulator. Air is a poor conductor. If it's windy, this layer of air will be moved away, and our body will have to heat that layer of air again. That makes us feel colder. So, if the wind is strong, the wind chill can be much lower. Alright? The heat index is very similar to this, except for our bodies to stay cool, they have to sweat. The reason they sweat is our body heat heats the water on our skin, causing this water to evaporate, and we cool off. So, what is the heat index? Well, if there's high humidity, evaporation does not happen so easily. So the more humid, the less evaporation, the hotter we feel. This is what we refer to as sensible temperature. So, okay, here comes everything you ever wanted to know about how we have to measure temperature in the atmosphere. So, I'm assuming you're familiar with the thermometer. It's a liquid in a glass, and as the liquid in the glass heats up, as it expands, and it changes temperature. So, they have these devices to record maximum temperature because they can only record these at particular times in the day. So this is a maximum temperature thermometer. It has a restriction right here. As the liquid gets pushed up, and it gets pushed up when it hits a maximum, and then when it cools off, it doesn't go back down so easily. And you can come back at any time to figure out what the maximum temperature is. And the way they reset it is they spin it, and it forces all the liquid back into the bowl. Now, minimum temperature is a little bit different. So we want to find out when this is a minimum. So they have this index marker, and as the temperature goes down, as this meniscus hits this, it moves this down, and when it warms back up, the liquid in the temperature bowl and the thermometer will move around this, and so this will stay put and mark when the temperature is a minimum, and that's this leading happens at this leading edge here. So what liquids do they use? Mostly they're now alcohol thermometers. Back in the day they used to be mercury thermometers, and that has not been placed. So this minimum temperature thermometer has to be horizontal in order to work. To reset it, you tip it upside down again and let this meniscus move this index marker back down. Alright, so they have electronic versions of these thermometers now. One is based on electrical resistance. The resistance of the wire depends on the temperature. So if you can measure the resistance, we can infer that to temperature. There's a thing called a thermistor. It's a ceramic material whose resistance increases with temperature. So again, you measure the resistance, you can measure the temperature. There's a device called a thermocouple. Basically, the temperature difference between the junction of two dissimilar metals creates a weak electrical current. You measure that current, you can determine the temperature difference, and that will allow you to determine the temperature. You also have radiometers and infrared sensors. These are more passive. This does not measure the temperature directly, or should I say does not measure the average kinetic energy of the molecules in the air. What these measure is the amount of infrared radiation being emitted by a particular object. And from that, you determine the temperature. You have what's called a bimetallic thermometer. You have two metallic materials that are stuck together that expand and contract differently depending on the metal used, and this will deflect this piece of metal as it heats up and cools, and then this deflection can be plotted on a chart. You'll have a thermograph. So this is basically a biometric thermometer, but the chart is on a drum, and this drum rotates, and as the drum rotates, the pen records the temperature at particular times. So this gives you a record of the temperature throughout the day. Alright, so this ends the lecture on temperature, or on seasons and daily temperature. Hopefully you have a better understanding on how, on what affects the seasons, about the Earth's orbit and the Earth's tilt. What local conditions can affect temperature, how the daytime affects the temperature of the atmosphere, how nighttime can affect the temperature of the atmosphere, how to take the temperature of the atmosphere, what controls the temperature of the atmosphere, what other things can control the temperature of the atmosphere, what is an isotherm, how temperature data is recorded, other factors that affect your sense of temperature, basically wind chill and heat index, and some of the instruments you can use to measure temperature. I'll see you in class on Monday.